people feel uncomfortable with complex numbers. They call it the imaginary number, but the reality is that you just didn't use it as much. You're pretty comfortable with square root of 2. If you think of square root of 2, that's just a symbol that denotes the solution of x squared equals 2. That's all it is. It's a symbol. You don't really know it exists. We're proving that in real analysis. You just know that it's the solution. You really only know that it's the solution of x squared equals 2. That's really what you know. And you've used that symbol so much that you're used to it. So if someone sticks up square root of 2, you know what a decimal expansion might look like for that to some point. You might know some things about it, you know, but primarily the definition of square root of 2 is that it's the solution of x squared equals 2. Just like that, we could also define I as being the solution to x squared plus the root to x squared plus 1 equals 0. That's the definition. You're just not used to using it as much. If I had my way, I'd teach MA 103 right at the start. Heck, I'd teach pre-calculus starting with matrices and introduce complex numbers right away. That way people get used to it. So some differences between the real numbers and the complex numbers. There's something called a field. And you're given this field in David Lay's book. They talk about field. The scalars come from a field. Fields are something that come from abstract algebra. Great class, by the way. If you want to take that class, it's awesome. But real numbers are the first field that are closed under taking limits. That means you can have a sequence inside R that remains inside R. The limit remains inside R. And that's what the real numbers is all about. That's why you work on the reals so much, because calculus is about taking limits. That's what you do. Why bother taking 104? I just explained calculus right now. This is really about taking limits. Real analysis is the study of limits. Abstract algebra, on the other hand, is the study of roots of polynomials. That's what that's about. Let's see if I have. And it's a travesty you don't have to take complex analysis as a requirement. You should take it. It's a really good class. It's not true for the rationals. You might think the rationals are a pretty big set. Rationals are the set of all numbers that are fractions, basically of the form P over Q, where Q is not 0 and P and Q are integers. But you have this famous, I wanted to actually prove this for you again. You've seen it before. It's one of my favorite little proofs using a natural log. But this sequence, you can just run it on Excel. Every single one of these sequences, elements are going to be fractions, but it's going to converge to Euler's constant, which is not a rational number, which I'm not going to prove that here, but maybe we'll prove it in there. That's all in Q. That's not in Q. So it's not closed under limits. So it's pretty unsatisfactory. Think about how you learn math. You start off with just counting natural numbers, 1, 2, 3, 4, 5. I think in kindergarten you have to count all the way up to 100. That's like one of their objectives. And then eventually you go to negative numbers. So you start with integers, both sides of the plane, both sides of the number line, and then they do fractions. And that's the rationals. And then they slap you upside the head with algebra and pre-calculus with Sol and the reals. Like, you're just going through the number systems and then looking at like extending each one. And every set you have includes the one before, right? The reals includes the rationals includes the integers includes the natural numbers, so they just move it up. R is the smallest field that contains all of its own limits. That's what it is. C is the smallest field to contain all of its roots. X squared plus 1 is a polynomial with coefficients in the integers and That's a pretty simple thing to write down, but its roots are not in z. Z is the integers. If I ask myself, what ingredients would I have to put into z so that I make it a field, so it has all these nice properties and I can do algebra on top of it, the answer you get is C. You don't get R, you get C, the complex numbers. All possible linear combinations of things that include I. And that's why you learn A plus BI as your complex numbers. That's all possible combinations of I, linear combinations of I. Very good? All right, John von Neumann actually said this. I think they mentioned his name in the Oppenheimer movie. A famous mathematician, did a lot of things in mathematics, but he said in mathematics, you don't understand them, you just get used to them. I use that quote a lot. You don't really learn math, you just kind of get used to it. If you don't believe me, try to teach someone how to do long division. You know, I had a neighbor's, the neighbors always come over when they have help, need help with their kids. And this fourth grader's mom came over with her daughter and said, we need help with long division. Like, I don't think I can teach that. I don't even know how to teach that. I'm so used to it. Okay, so here we go. Suppose you have y double prime plus y is equal to 0. You see where I'm going with this. This is going to give you a characteristic equation with my famous x squared plus 1 is equal to 0. And I have two initial conditions, y0 is 1 and y prime as 0 is 0. And I'm going to put it in matrix form. So you've seen this maneuver. You don't really learn things, you just get used to it. That's why we're doing this. We're going to get used to it. And you get this matrix equation. So the coefficient matrix, the eigenvalues of the coefficient matrix, that is so easy. You can actually subtract lambdas down the diagonal and then do it the way you did. Where do you guys learn it? Where do you learn eigenvalues? Other than just linear algebra? 153? Okay. But I was lazy. I just Google searched and said, give me the eigenvalues. Nothing wrong with that. So you're going to rewrite all your lambdas, your eigenvalues, as a plus or minus bi. And by the way, that's a great proof to do in abstract algebra that if one complex number is a root, its complex conjugate is also a root. So they're going to be both in there. So they're going to come in pairs. And by the way, I didn't go to Mathematica. I just Google search, give me a calculator that gives me the roots of it, the eigenvalues of 2 by 2. As I just took the first hit. And then you write down the general solution. And I'm going to tell you why the general solution is like this after we actually do the work. So once you write it like this, the A's and B's pop in place. You might be surprised. All of a sudden, you're getting cosines and sines. Really cool formula called Euler's formula that makes this true. However, I'm not going to go into it as we actually do problems. So your solutions are going to be of the form of cosines and sines. So you get something very different when you have a complex eigenvalue compared to what you got with the imaginary part not 0, right? Because real numbers are also complex numbers with the imaginary part 0. You get oscillatory behavior. And then yada, yada, yada. Plug t equals 0 into your general solution to get the first equation to get rid of your C1, C2s. That was given to us. And, you know, just in case you forgot your trig, you should never forget your trig. That's something that you should remember. So I always recommend getting a tattoo of the unit circle. You're allowed to wear tattoos in the Army, right? So you can get a tattoo of the unit circle, and you will be the life of the party. Tell me about that tattoo. And you'll never forget the unit circle. It'll always be there.
What does it mean solving or to get the first equation?
When you plug in your first initial condition, you'll get one equation, and then you have two initial conditions.
So we're getting rid of C1 and C2.
Yes. Just, that's why I said yada, yada, yada. You're used to this. And so I have C1. I haven't told you this, but if you're doing things manually, anytime you solve something, get rid of it right away because it makes your math easier. And then you plug t equals 0 into the second initial condition, and you'll get C2 is 0. And then you write down your particular solution. So your y of t is cosine t. So we're going to try one. I think I gave you one to do. Yeah, I thought you guys would be mad at me if I copied and pasted this example and put that here, because this was really easy. So I put a harder example so you can see it.
I would have preferred that.
Yeah, nobody gives you easy things. Or do they tell you this? You didn't come to West Point to do easy things.